Hi! In one of the last episodes I presented this small FPGA board and how it could be used to decode the Behringer Ultranet protocol. Thank you for the numerous emails and messages in the DIY audio forum. Today I want to conclude the FPGA-based system and enhance it to do even more audio processing. Until now we only decoded the I2S-like audio stream, adjusted the volume and then directed it to the stereo output. But the integrated FPGA has much more logic elements available than we are currently using. A few things are still missing for a real and modern audio mixing console. Last time I used the PDM output to convert the digital audio back to the analog world. Here we need to check if the signal has a good audio quality or we have to do more optimizations. So we have a lot to do today. First, I'd like to introduce my today's sponsor, me. I make these videos completely independently and without any intention of profit. If you like the videos, I would be happy about a subscription or a few comments from you down below. Back to the topic. If we only adjust the volume of an audio source, real instruments may sound okay, but we do not have any control over the sound. Mr. Bassman, please give us some bass riff. This was recorded using a standard dynamic microphone in front of the amplifier. Sounds okay for me, but we need at least a sound configuration option like an equalizer if some more instruments will come up. When playing the trumpet, you have to breathe, and so you will hear the breathing noises. So we should try to implement a noise gate to get the noise under control. Modern mixing consoles also offer a dynamic audio compression and an audio crossover for subwoofer and the tweeter. But let's take a look at the equalizer first. With current mixing consoles, you can not only boost or cut individual frequencies, but also adjust the sound graphically. Most channel strips offer 3 to 5 options here, which you can then switch between peak filter, shelf filter, cut filter and so on. So how do we implement this in the FPGA logic? Two approaches can be used here: infinite impulse response filters, IIR filter, or finite impulse response filters, FIR. Although FIR filters are more stable than IIR filters, they require significantly more memory and computing resources. That's why we should take a closer look at the IIR filters first. With these filters, 2 or more previous samples are used to weight them with coefficients. This becomes a little clearer in the graphic of a so-called biquad IIR filter configuration. Here we have a forward path for the input samples and a feedback path for the output samples, each with individual multiplicators called coefficients. Plotted as an equation, this looks like this. From the samples coming in every 20.8 microseconds at 48 kHz, we first use the current input sample x0 and multiply it by the coefficient a0. We then repeat this for all previous samples. Finally, we have to take the output signals into account as feedback and subtract it from the input samples. However, this is now quite unreadable, so we calculate the sums. This is exactly what we have to implement in the FPGA now. So there are 3 additions, 1 subtraction and 5 multiplications for the individual coefficients. For this, our Cyclone FPGA offers dedicated 9-bit multipliers. Since we want to process our audio data with 24-bit, we need at least 3 DSP multipliers for each multiplication. In fact, we even need more multipliers as the coefficients unfortunately require quite high resolutions. With the online biquad calculator we can easily calculate the individual coefficients. As you see, all values are significantly smaller than 2.0. Before we can implement this, we have to deal with the fact that our FPGA does not have any kind of floating point unit. That's a bit challenging as we have to calculate the whole numbers using fixed point arithmetic. There is a whole series of YouTube videos on this, but to summarize briefly, we multiply our small numbers by a freely chosen value to the base of 2, perform the multiplication and at the end shift the result back to the right by the chosen number of bits. Now we have to get this implemented in the logic. All 5 multiplications together require 20 DSP slices, which is almost 20% of the available 112. Therefore, we will design the VHDL code in such a way that we are using the same multiplicators in a process and thus only use a single multiplication several times. First, we define our file header part with the ports for input and output. Then we can set up the universal multiplication process. In the main part, we then need a small state machine which calculates all 5 multiplications and additions within 5 states. In the last state, the result is then switched to the outputs. A synchronization bit is set and the shift register for output and input signals are updated. The coefficients have already been multiplied by 2 to the power of 30 in order to be able to perform the integer multiplication. Without comments in the code, that's a total of 81 lines, which are processed at 100 MHz within 60 nanoseconds. Pretty impressive. That means we can work in real time with only one sample latency, as 20.8 microseconds between the individual samples are way longer than our process time. For a stereo EQ, these calculations have to be calculated twice, but can be carried out in parallel, one of the biggest advantages of an FPGA. For several EQs, the output of one EQ block is then connected to the input of the next EQ. For 5 equalizers, we then need around 300 nanoseconds, but this is still way below the 20.8 microseconds. Well, then let's test the EQ. Compiling the Quartus project takes around 1 minute, and now I will take the slightly modified Arduino code I've shown in my previous video about this FPGA project to upload the bitstream via the onboard SAMD21 Cortex-M0 controller into the FPGA. But we still need to calculate the coefficients when changing the EQ settings. For this we will use the onboard ESP32, which also sits on the Vidor 4000 board. Last time we only used it to adjust the volume. Now we calculate the coefficients in the function recalc-filter-coefficients-peq. Here I've implemented all regular filter types: peak filter, a bandpass filter, shelf filter, as well as high and low pass and a notch filter. For testing, let's take a simple peak filter. In addition to the frequency, we also have the Q factor and the gain. After the calculation and conversion into a Q30 number for the integer arithmetic with 30 bits for the fraction part, we send the 5 coefficients via UART to the FPGA and forward the values as bit vectors to the IIR blocks. The ESP32 can be programmed via the UART connection through the SAMD21 with the regular Arduino IDE. Now we can test the new EQ section, right? Well, so far we don't have a proper connection to send our EQ settings to the ESP32. Of course, there are terminal apps like HTerm for sending strings via UART. But since I'm not only a fan of audio technology, but also of retro computing, wouldn't it be great if the whole thing could be controlled via an ancient user interface? We've been working with VHDL for a while now, so a little trip into computer technology will not hurt. My first computer was an Intel 486 with Windows 3.11 and IBM's OS/2 in a dual boot. In fact, I still have that exact computer here. Well, the hardware. The case has been lost in the past 30 years. Since I had good experiences with Borland's Delphi 7 when programming the PC dimmer program, and I also have a valid license for Delphi 1, I actually wanted to write an app for Windows 3 with this Delphi version and run it under OS/2. Well, OS/2 can run Windows applications via a special WinOS2 layer, but not natively, so this would be a kind of cheating. There are also the Windows libraries for OS/2 called Willow, with which you can run a Windows 3.0 application natively under OS/2 and its presentation manager. At first glance it sounds like a nice idea, but if I had known how much effort it would mean in the end, I probably wouldn't have done it. To let OS/2 know that an application is to be started using the Willow translation, the header of an exe file, or new executable file, can be adapted accordingly. Here, the OS2 EXO flags must be set to hex value 80. This can be done using a regular hex editor, but I have also written a small app for this. Unfortunately, Delphi 1 apps require the toolhelp DLL, which was only introduced with Windows 3.11, which is around 1 or 2 years younger than the Willow library. I tried to write a wrapper DLL, as the toolhelp DLL seems to use only functions from kernel and user DLL, but unfortunately the Willow kernel does not have all the required API interfaces for Windows 3.11 applications. In short, I had to write an application especially for Windows 3.0 using Visual C++ from 1993. But finally, this should run under OS2 using Willow. Let's give it a try. This brings me to another problem. In 1994 there was no USB thumb drives and no CD. Only the zip disk remains. But this is not available on my current computer, so we have to make a time travel through several decades of computer technology to transfer the necessary files. We are back in the year 2004 and we try to copy some files from the USB thumb drive to the zip disk. That's looking good. But now we have to go back in time one step further to 1994. Look at this wonderful user interface, great. But we have a lot of work to do, so let's copy files from this zip drive to our 1994 486. Woohoo! We have a native OS2 Warp application, great. But while testing this app I realized that OS2 Warp 3 cannot handle UART baud rates above 57.6 kilobaud. On my real 486 it was even lower and supported only 38.4 kilobaud. My Warp drive seems to be running out of dilithium. I had to install the latest fix pack from IBM and exchanged the UART driver from OS2 with a new one to get 115.2 kilobaud. Those were rough times and many things transfigure over time. But finally we can test our new system now. I connected everything to a breadboard with loose cables, but it's fine for testing now. I connected an SD card, an OLED display to see what our system is doing, but everything can be now controlled via our user interface. So let's start with some music. So first I will try a peak filter. Maybe we can increase a bit more the heights. Okay, let's try some drums. Well, that sounds pretty decent. However, this is still not the typical sound that we know from today's audio recordings. The missing magic words are dynamic audio compression. This automatically reduces the volume of audio samples above a certain threshold. The level of compression can then be set via the ratio. As the audio signal loses level with stronger compression, the volume can be increased again using an additional gain called makeup gain. What exactly do we need to implement this now in the FPGA? Well, first of all, the ability to set the volume automatically, meaning another multiplication for at least 24 bits. To calculate the gain, we first need to compare the absolute value of the audio signal with a given threshold signal and calculate the overshoot. This overshoot is then used as the base for the necessary compression and results in the desired gain normalized to the sample. Unfortunately, there is now a crucial difference to the equalizer if we look at the equation. We need a total of 2 divisions. However, divisions, unlike multiplications, are considerably more complex to implement in FPGAs and have no hardware support in smaller devices like our Cyclone 10. However, if we only set the ratio of the compression in ranges of 1/2, 1/4, 1/8 and so on, we can use simple bit shifting to the right here and can remove one of the 2 divisions. But to calculate the actual gain, we still have to divide in order to obtain a sufficiently good resolution. Here we can use the so-called radix 2 division, which is carried out in a separate process. The state machine of the compression remains in the division state until the busy flag of the division process changes to 0. This may take a little longer, but we still remain well below the 20.8 microseconds. Finally, we need a low-pass filter, which is a simple filter that determines the rate of changes per time with a single coefficient alpha. This coefficient depends on whether we are in attack or release mode. The file structure of the compressor is similar to the equalizer. At the beginning, we again need the basic definition of the file. In addition to the multiplication process, we now also define the process for the division. The state machine is then again synchronized with the main clock. To begin, we compare the absolute value of the input sample with the threshold signal and then load the division process. After this, we need to check whether our compressor has already been triggered or is in hold or release mode. Overall, the VHDL file of the compressor is about twice as large as that of the EQ. Instead of 81 lines, we now need 153 lines without the code of the division. Before we can test the new audio block, we need to calculate a few more parameters: threshold, ratio and the timings for attack, hold and release. For this, I've implemented the function recalc compressor within the ESP32. The compression ratio is rounded to the values of the base of 2 so that we can easily use a bit shift for the division here. We then calculate the subsequent makeup gain using a bit shift to avoid a second multiplication. Although we only have rough 60B steps here, this is sufficient for now. As the low-pass filter has the sample rate of the audio signal as its time base, we must take this time of 20.8 microseconds into account when calculating the attack and release coefficients. To calculate the coefficients, we use the typical 10%, 90% limits from control engineering, which we must consider using the logarithm. This value multiplied by the desired time results in our coefficients alpha when using the E function. For the sake of simplicity, the hold time is simply counted as the number of sample ticks so that we can multiply the desired hold time by the sample rate. Now we have a very powerful audio tool to shape the sound. Let's try it out with different settings. Well, we have already achieved a lot and implemented a complete channel strip now. A noise gate can also be implemented as it is calculated almost identically to the audio compression. Only the division is no longer necessary, as we only have to open or close the gate when a threshold is exceeded, but no longer change the gain depending on the overshoot. This simplifies the calculation to a comparison with the threshold, the low-pass filter for gate open and gate close, and the multiplication. Okay, you can now hear me through this microphone from the ADC connected via I2S. And now I'm reducing my hold time. You can hear now my noise from a computer in the background. And you can hear after 500 milliseconds the noise will go down. So increase the release time to about 400 milliseconds. And then it's fading out. In the last FPGA video, I only applied the PDM signal to the line input of my audio interface, played it back briefly and didn't look at it any further. Today we should check whether a simple RC low-pass filter can really form a good signal from a pure digital output. So let's test with a very low frequency, starting at 50 Hz, so a very good bass. And as you can see, we result very good 50 Hz signal here with a very simple RC filter. So let's go higher, 150 Hz. Seems to be fine too. Increasing even more. So increase to 5 kHz. As you can see, some problems are starting to rise up here, and we still have a sinusoidal waveform, but within the sine wave we have some steps. And this is the problem with our zero order hold here in the FPGA, because we are getting new samples only every 20.8 microseconds at 48 kHz. And our PDM is working at 5 MHz. So our PDM is much faster than the samples getting in. So 10 kHz. Yep. This is hard in sinusoidal waveform. And now even more, 16 kHz. This is more or less garbage. To solve this problem, we can use a steep low-pass filter with a sample rate of the PDM modulator to achieve better results, as sharp edges can only be represented by high-frequency parts. To do this, we again use an IIR filter to cut off everything above the maximum usable frequency. With a sample rate of 48 kHz, the Nyquist frequency is 24 kHz. So we can place the filter somewhere around 28 kHz, remembering that there is a 3 dB attenuation at the designed frequency of the filter. If we now feed this signal to the PDM modulator, we get a much smoother signal, as the hardware low-pass filter has much less work to do. So I uploaded everything, and let's start again from 5 kHz on. Yeah, and there are no stash steps anymore. So our filter is doing what it should do, and let's increase to 16 kHz. So frequency at 16 kHz, and the sine wave is quite fine. In the end, we can check how good our system is in terms of frequency response by looking at the frequency spectrum. In a perfect world, we will only obtain peaks at those frequencies at which we also excite the system. So let's have a look at the signals in the time domain and the frequency domain. The FFT is configured that we can see 0 kHz up to 25 kHz. And let's start at 50 Hz. At the very end of our FFT, you can see one small dash at 50 Hz. Sorry, I cannot configure any logarithmic scaling on the horizontal line, but we will see it a bit better with higher frequencies. Let's go up at 150 Hz. Everything fine so far. Increase to 1 kHz. Well, everything fine. Go to 5 kHz. Go up to 10 kHz. Still okay. And 16 kHz. Well, for 16 kHz there seems some disturbances in the frequency domain, but this is not a problem of our PDM or our RC filter. It's a problem with the format I've chosen here for these tests. I'm using MP3 format, and MP3 has some drawbacks for higher frequencies, so let's start a signal using uncompressed wave files. And here we are using the same 16 kHz signal, and then the spectrum is quite fine. So our PDM with the IRR filter seems to make some good work here. One last test I'd like to do here with this spectrum analyzer and playback a multitone. So using 1 kHz, 5 kHz, 10 and 16 kHz at the same time. So load the uncompressed wave file. And here we can see in the spectrum our 1 kHz, 5, 10 and 16 kHz. And our low pass seems to do a good job here. In comparison, we can take a look at the same thing with a commercial available SPDIF DAC converter. So I start the multitone, and as you can see, the peaks in the spectrum are quite comparable. At 1 kHz, 5, 10 and 16 kHz we have the main peaks, and between the main peaks we have harmonics. The only thing you can see in direct comparison, we have a lower amplitude in the upper peaks. So at 10 kHz and 16 kHz with our very simple RC filter together with the IIR filter in the FPGA, we have a bit damping at the higher frequencies. In my opinion, this result is great for a DIY project. In the end, the PDM itself has a signal-to-noise ratio of around 85 dB, resulting in an effective 14-bit DAC, but should still be more than sufficient for most applications. Alternatively, a small SPDIF converter could be used. The unbeatable thing of an FPGA is that all the individual logic parts can be recombined, exchanged or removed with little effort, and that the whole system processes the audio signals in real time. This means that there is no 10 to 20 milliseconds latency like in a classical computer, but the entire audio processing is calculated within a few microseconds, and the input signals are at the output after just 1 or 2 audio samples of delay. You can find more information about this project on my GitHub page. There I have published the entire source code, including a modern web interface, SD card playback of MP3s and a small display with a menu structure. With this you should be able to create your own 22-channel audio mixing console with a plenty of new functions. After so much work on an audio mixing console, we should conclude this episode with some more music. I used our new fancy FPGA tool as an external insert effect for my trumpet. Maybe I will spend a bit more time developing a reverb, but for now the other effects were processed by the Audio DAW. In 1989, Capcom released a game for the Nintendo NES in which one track is really catchy. From DuckTales, The Moon. See you next time.